Welcome to Engineering Studio with Dr. Mohammed Tahir. In this video, we are going to discuss about the flow chart for design of compression members. So first of all, the input data. So in case of compression member, we need the input data like dead load, live load, and end conditions. Then calculate PU by using critical load combination. So calculate the PU by using load combination like 1.2 dead load plus 1.6 live load. And also find the effective length factor Kx, Ky, and Kz depending upon the end conditions. So after that, we need to assume the slenderness ratio to actually select the section. So here we have a guideline. For single angle, we can assume R is equal to 125, for channel section 115, for double angle or W section 90, for built up sections like double C back to back or face to face, we can assume 70, and for section continuously braced in the lateral direction, we can use R is equal to 35. So we need to initially assume the slenderness ratio value, because at that stage we do not know the dimension of the section. So once we have the slenderness ratio, so based on that assumed slenderness ratio, we need to calculate this phi c FCR. So here we have two methods. Either we can go to the LRFD manual and we can find the phi c FCR value corresponding to the assumed slenderness ratio, or otherwise we need to compare that the assumed slenderness ratio whether it is less than or greater than RC value. So for example, if it is less than RC value, it means we have inelastic buckling. So in that case, FCR will be equal to 0.685 Fy over Fe into Fy. So we need to confirm this factor. So it is just like this. We have seen in the previous video what is the formula for FCR in case of inelastic buckling. So by using this expression, we can calculate the FCR value. Then phi c will be equal to 0.9. So by using this expression, we can calculate the phi c FCR value. So once we have phi c FCR value, then we can calculate the area required, because we know phi c Pn is equal to phi c FCR Ag. So it should be equal to Pu applied load. So we can write that Ag is equal to Pu over phi c FCR. So from here we can calculate the required area. So once we have the required area, we also need to calculate the minimum B minimum. So that is based on the connection detail, whether one leg is connected or both legs are connected, or in case of channel section, flange as well as web are connected. So if for example only one leg is connected, so we can say it is 2.5 times diameter of rivet plus 16, and if both legs are connected, it will be 3.25 D plus 18. So by using these expressions, we can calculate B minimum. So we need to select the section based on these two values, area required as well as B minimum. So selection should be such that area selected should be more than or nearly equal to area required, as well as the width of the section or width of flange should be more than B minimum. And we should select a section which has minimum possible weight, and we have a guideline that in case of W section, the depth of the section should not exceed 360 millimeter. So this is just a guideline. So we need to satisfy these three criteria. The area selected should be nearly equal to area required. We should go for the section with the minimum weight, and the width of the section or the width of flange should be more than the B minimum value. So once we have the section, then we need to determine the slenderness ratio of the section to apply the global instability check. So we need to calculate the critical slenderness ratio for that case. So we have already decided the K value, Kx, Ky, and Kz based on the end conditions, and we also have Ly, Lx, and Lz value. If there is no bracing, then it will be equal to the total length of the member. But if there is a bracing in any direction, so we can need to consider the corresponding value of Lx, Ly, and Lz. Okay, so once we have K value and L value, then we need to determine this R value, or we can directly select these values from the table of LRFD. properties of the section, or we can calculate the radius of gyration in x, y and z direction for the selected section. So once we have these three values k, l and r, so we can easily calculate the slenderness ratio value. So the largest value out of these three will be our selected or required value or critical value, the highest out of these three. So r will be equal to maximum value out of the above slenderness ratio x, y and in z direction. So if we have a single angle or W section, or we can say if it is not a built up section, then we need to proceed directly to the local instability check. We need to perform the local instability check. We need to check that B over T value for unstiffened and stiffened element mean if we talk about the flange, it is unstiffened and the web is stiffened element. So we need to perform the stability check, local stability check for these two values. So B over T should be less than lambda r. Similarly, H over TW should also be less than lambda r. So we need to perform this local instability check. And after performing the local instability check based on the critical slenderness ratio, and that critical slenderness ratio should be less than 200. So based on this slenderness ratio, again we will calculate phi CFCR and we will multiply it with the selected area or the area of selected section, and it should be more than PU, the applied load. Otherwise, if it is less, then we need to revise the section. We need to go for the higher section with the higher area or with the lesser slenderness ratio. And if there is stress reversal, then we will see if TU is greater than 0, mean there is tensile stress as well, or tensile load is also acting on that section. So in that case, we also need to perform the check that the tensile capacity should be more than the tensile load. Finally, we will check for the loading cycle for the fatigue strength, and if it is less than 20,000 cycles, so it's okay. Otherwise, we need to go for the design. So this is for single angular section which is not a built up section. But if we have a built up section, so in that case we need to perform some other calculations. We actually need to design the stay plate in case of built up section. So after calculating the R in all the three directions X, Y and Z, we need to design the stay plate. So in case of built up section, so for example we have built up section like this. So we use these stay plates at different intervals. So if the distance between these stay plates is equal to A, then we need to determine the slenderness ratio of this section, individual section between these stay plates. So A over R minimum of this section X, Y, R, Z, whatsoever is the minimum. So it will give us a slenderness ratio, and this slenderness ratio should be less than or equal to 0.75 times R. So it should be equal to or less than 0.75 R. So we need to design the spacing A in such a way that we can satisfy this expression. So after satisfying this expression and selecting the value of A, mean we have decided how many stay plates will be used and what will be the spacing between these stay plates. And one thing we need to keep in mind that the spacing between the stay plates should be uniform. Between the all stay plates, the spacing should be uniform, and we can only go for 2 or 3 stay plates. We cannot use more than 2 or 3 stay plates in case of built up section. So when we use stay plates in a built up section, then we need to calculate the modified slenderness ratio of the section. So to calculate the modified slenderness ratio, we have already studied in the previous video how we can calculate the modified slenderness ratio. We calculate A over R value and then we calculate the slenderness ratio. So for snug tight connection, it is KL over R square plus A over R square root. So the other formula is also explained in the previous video. So by using this expression, we can calculate the modified slenderness ratio. So now we have 4 slenderness ratio of the section, or we can say 5 slenderness ratio: Rx, Ry, Rz. It may be or may not be. In case of unsymmetrical section or angle section, we also have minor axis, Z axis. Similarly, A over R and R modified. So all these should be less than 200. So definitely this should be less than these three values. It should be maximum up to 75% of the highest value of these three. Similarly, this modified slenderness ratio or the highest slenderness ratio out of these three, it should be less than 200. If it is satisfied, it means the global instability of the section is satisfied. The member will not buckle globally. Then after performing these checks or the global instability check, we need to go for the local instability check. So the remaining procedure will remain same. Only in case of built up section, if we are using stay plates, so we need to do this exercise. That first we need to decide the spacing between the tie plates or stay plates, and then we need to calculate the modified slenderness ratio. And then based on the modified slenderness ratio or the highest value out of this R and RM, we need to calculate the capacity of the section. So we need to check it for the global instability. It should be less than 200, and then we will calculate the capacity of the section based on that slenderness ratio, and the remaining procedure will remain same. If we are using stay plates, so in that case we do not need to calculate the modified slenderness ratio. Rather, we will directly go to the design of lacing. So that will be covered in the next video, how we design the lacings.